Welcome back, everyone, after the short break. I know that many of you are looking forward to hearing from our next speaker, Jensen Huang. Jensen is at the cutting edge of artificial intelligence and all of the innovation, technology, and human capital that is needed to support it. My good friend and SIEPR colleague, John Chauvin, is going to introduce Jensen, and I hope he's here somewhere, so I'm just going to keep talking. And then the two of them will have a conversation before taking some of your questions. John Chauvin certainly requires very little introduction to most in this crowd. As my predecessor as the Trione Director of SIEPR, John is the one who started the SIEPR Economic Summit 20 years ago. So I would just like, right now, for all of us to give John Chauvin a huge round of applause and appreciate the community. That he had the foresight to build. For those of you who haven't been touched by John's research, his mentorship, or his friendship, here's just a snippet of what you might like to know about him. Along with being the former SIEPR director and a SIEPR senior fellow emeritus, John is the Charles R. Schwab Professor of Economics. He is also a senior fellow at the Hoover Institution and a research associate of the National Bureau of Economic Research. He specializes in public finance and corporate finance and has published many articles over the years on Social Security, health economics, corporate and personal taxation, mutual funds, pension plans, economic demography, applied general equilibrium economics, and much more. John isn't one for long introductions, but I just will say that if I can be 1/10 as helpful to my successor as John has been to me, I'll feel like I've succeeded. So I will let you read more about his publications and accomplishments in the programs you've received today. And so please join me in welcoming our good friend John Chauvin, and I'm really looking forward to it.
Thanks. Wow, thank you. So I have always thought that the more famous the speaker, the shorter the appropriate introduction. And if I was to follow that rule, I would stop right now and say Jensen Huang. But I'm not going to do that. So the Oxford English Dictionary defines the American dream. Believe it or not, it does that. And it says that it's a situation where everybody has an equal opportunity for success through hard work, dedication, and initiative. And I would like to say that Jensen Huang is an example of the American dream. Jensen was born in Taiwan, came to the U.S. at age 9 with his brother, not with his parents, went to a rough, tough school in Kentucky, survived that. His parents came 2 years later. He moved to Oregon, skipped 2 grades and graduated from high school, and went to Oregon State, electrical engineering major. 150 men and 2 women. He said he was 16, he looked like he was 12, he had no chance with the women. Well, he sort of liked one of them and said, why don't we work on homework together? And did that over and over and over again. 6 months later, he asked her out for a date. Well, he's still married to her. So, another American dream. Now, to skip to age 30, he co-founds NVidia. He's the only CEO there's ever been of NVidia. It's had its ups and its downs, more ups than downs. It's now the 4th largest company in the world, 3rd largest American company. So that sounds to me like the American dream. I should add that he also got a degree from Stanford, master's degree. I think he did it mostly at night. And he was always good with homework. At work with his wife, at work with Stanford, too. Now, of course, we're here. Last week, NVIDIA announced its earnings. In the finance crowd, this got more attention than the Super Bowl that occurred a couple of weeks earlier. It was pretty amazing. His company is at the absolute center of the most exciting development, I'd say, of the 21st century, technology development. And so he's to be congratulated on that. Let me just say, he's received a lot of awards, a lot of recognition. NVIDIA's received a lot of awards, a lot of recognition. But I should have a short introduction, so I'm about to quit. I'm just going to talk about one award. Last month, he was elected as a member of the National Academy of Engineering. This is a pretty prestigious award. There are only 3 that I know of. I actually asked ChatGPT, I didn't get an absolute clear answer. How many CEOs of S&P 500 companies are members of the National Academy of Engineering? But I think it's 3. And 2 are in this room. Anirudh Devgan of Cadence Design Systems was awarded it last year. So the 2 of them have that in common. But let me now just conclude and congratulate Jensen, not only on this award, but on the amazing success of your company, and thank you for speaking to us today at SIEPR. Jensen. I'll sit here.
Thank you.
Thank you.
You're here, I'm here?
I guess so.
Okay.
So why don't you start off with maybe some opening remarks, and then I'll ask you a few questions, and then you get the tough questions.
Well, I think that after your opening remarks, it is smartest for me not to make any opening remarks to avoid risking damaging all the good things you said. But let's see. It's always good to have a pickup line, and mine was do you want to see my homework? Yeah, and you're right. We're married still. We have 2 beautiful kids. I have a perfect life, 2 great puppies, and I love my job, and she still enjoys my homework.
Well, if you want, I can ask you a few questions then.
Yes, please.
So, in my lifetime, I thought the biggest technology breakthrough was the transistor. Now, I'm older than you. Yeah. And it was pretty fundamental.
It's a big deal, yeah.
But should I rethink? Is AI now the biggest change in technology that has occurred in the last 76 years? To hint at my age.
Yeah. Well, first of all, the transistor was obviously a great invention, but what was the greatest capability that enabled was software. The ability for humans to express our ideas, algorithms, in a repeatable way, computationally repeatable way, is the breakthrough. What have we done? We dedicated our company in the last 31 years, to a new form of computing called accelerated computing. The idea is that general purpose computing is not ideal for every field of work. And we said, why don't we invent a new way of doing computation such that we can solve problems that general purpose computing is ill-equipped at solving. And what we have effectively done in a particular area of a domain of computation that is algorithmic in nature, that can be parallelized, we've taken the computational cost of computers to approximately 0. So what happens when you are able to take the marginal cost of something to approximately 0? We enabled a new way of doing software where it used to be written by humans. We now can use computers to write the software because the computational cost is approximately 0. And so you might as well let the computer go off and grind on just a massive amount of experience we call data, digital experience, human digital experience called data, and grind on it to find the relationships and patterns that, as a result, represents human knowledge. And that miracle happened about a decade and a half ago. We saw it coming, and we took the whole company and we shaped our computer, which was already driving the marginal cost of computing down to zero, and we pushed it into this whole domain. And as a result, in the last 10 years, we reduced the cost of computing by 1 million times. The cost of deep learning by 1 million times. And a lot of people said to me, but Jensen, if you reduce the cost of computing your cost by 1 million times, then people buy less of it. And it's exactly the opposite. We saw that if we could reduce the marginal cost of computing down to approximately zero, we might use it to do something insanely amazing. Large language models. To literally extract all of digital human knowledge from the internet and put it into a computer and let it go figure out what the knowledge is. That idea of scraping the entire internet and putting it in one computer and let the computer figure out what the program is an insane concept. But you wouldn't ever consider doing it unless the marginal cost of computing was zero. And so we made that breakthrough. And now we've enabled this new way of doing software. Imagine, for all the people that are still new to artificial intelligence, we've figured out how to use a computer to understand the meaning, not the pattern, but the meaning of almost all digital knowledge. And anything you can digitize, we can understand the meaning. So let me give you an example. Gene sequencing is digitizing genes. But now with large language models, we can go learn the meaning of that gene. Amino acids, we digitized, through mass spec, we digitized amino acids. Now we can understand from the amino acid sequence, without a whole lot of work with cryo-EMs and things like that, we can go figure out what is the structure of the protein and what it does. What is its meaning? We can also do that on a fairly large scale pretty soon. We can understand what's the meaning of a cell. A whole bunch of genes that are connected together. And so this is, from a computer's perspective, no different than there's a whole page of words, and you asked it to, what is the meaning of it? Summarize. What did it say? Summarize it for me. What's the meaning? This is no different than a hard, big, huge, long page of genes. What's the meaning of that? Big, long page of proteins. What's the meaning of that? And so we're on the cusp of all this. This is the miracle of what happened. And so I would, it's a long-winded answer of saying, John, that you're absolutely right, that AI, which was enabled by this new form of computing we call accelerated computing that took 3 decades to do, is probably the single greatest invention of the technology industry. This will likely be the most important thing of the 21st century.
I agree with that. 21st century, but maybe not the 20th century, which was the transistor. It's got to be close. We'll let history decide.
That's right.
We'll let history decide. Could you look ahead? I take it that the GPU chip that is behind artificial intelligence right now is your H100, and I know you're introducing an H200. And I think I read that you plan to upgrade that each year. And so could you think ahead 5 years, March 2029, you're introducing the H700.
Right.
What will it allow us to do that we can't do now?
I'll go backwards, but let me first say something about the chip that John just described. As we say a chip, all of you in the audience probably, because you've seen a chip before, you imagine there's a chip kind of like this. The chip that John just described weighs 70 pounds. It consists of 35,000 parts. 8 of those parts came from TSMC. That one chip replaces a data center of old CPUs like this into one computer. The savings, because we compute so fast, the savings of that one computer is incredible, and yet it's the most expensive computer the world's ever seen. It's $250,000 per chip. We sell the world's first $250,000 chip. But the system that it replaced, the cables alone cost more than the chip, this H100. The cables of connecting all those old computers. That's the incredible thing that we did. We reinvented computing, and as a result, marginal cost of computing went to zero. That's what I just explained. We took this entire data center and we shrunk it into this one chip. Well, this one chip is really, really great at trying to figure out this form of computation that without getting weird on you guys, called deep learning. It's really good at this thing called AI. And so the way that this chip works, it works not just at the chip level, but it works at the chip level and the algorithm level and the data center level. It works together. It doesn't do all of its work by itself. It works as a team. And so you connect a whole bunch of these things together, and it works at, networking is part of it. And so when you look at one of our computers, it's a magnificent thing. Only computer engineers would think it's magnificent, but it's magnificent, okay? It weighs a lot, miles and miles of cables, hundreds of miles of cables. And the next one's soon coming is liquid cooled, and it's beautiful in a lot of ways, okay? And it computes at data center scales. And together, what's going to happen in the next 10 years, say, John, we'll increase the computational capability for deep learning by another 1,000,000 times. And what happens when you do that? Today, we kind of learn, and then we apply it. We go train, inference. We learn, and we apply it. In the future, we'll have continuous learning. We could decide whether whatever that continuous learning result, it will be deployed into the world's applications or not. But the computer will watch videos and new text and from all the interactions that it's just continuously improving itself. The learning process and the training process and the inference process, the training process and the deployment process, application process will just become one. Well, that's exactly what we do. We don't have between now and 7 o'clock in the morning, I'm going to be doing my learning, and then after that, I'll just be doing inference. You're learning and inferencing all the time. And that reinforcement learning loop will be continuous. And that reinforcement learning will be grounded with real-world data that is being through interaction, as well as synthetically generated data that we're creating in real time. So this computer will be imagining all the time. Does that make sense? Just as when you're learning, you take pieces of information and you go from first principles, it should work like this, and then we do the simulation, the imagination in our brain, and that future imagined state, in a lot of ways, manifests itself to us as reality. And so your AI computer in the future will kind of do the same. It'll do synthetic data generation, it'll do reinforcement learning, it'll continue to be grounded by real-world experiences, it'll imagine some things, it'll test it with real-world experience, it'll be grounded by that, and that entire loop is just one giant loop. That's what happens when you can compute for 1,000,000 times cheaper than today. And so as I'm saying this, notice what's at the core of it. When you can drive the marginal cost of computing down to zero, then there are many new ways of doing something you're willing to do. This is no different than I'm willing to go further places because the marginal cost of transportation has gone to zero. I can fly from here to New York relatively cheaply. If it would have taken a month, I'll probably never go. And so it's exactly the same in transportation and just about everything that we do. And so we're going to take the marginal cost of computing down to approximately zero. As a result, we'll do a lot more computation.
That causes me, as you probably know, there have been some recent stories that NVIDIA will face more competition in the inference market than it has in the training market. But what you're saying is it's actually going to be one market, I think. Can you comment about, is there going to be a separate training chip market and inference chip market, or it sounds like you're going to be continuously training and switching to inference maybe within one chip. I don't know. Why don't you explain some more?
Well, today, whenever you prompt an AI, it could be ChatGPT, or it could be Copilot, or it could be if you're using a ServiceNow platform, if you're using Midjourney, using Firefly from Adobe. Whenever you're prompting, it's doing inference. You know, inference is so it's generating information for you. Whenever you do that, what's behind it, 100% of them, is NVIDIA's GPUs. And so NVIDIA's, most of the time you engage our platforms are when you're inferencing. And so 100% of the world's inferencing today is NVIDIA. Now, is inferencing hard or easy? A lot of people, the reason why people are picking on inference is when you look at training, and you look at an NVIDIA system doing training, when you just look at it, you go, that looks too hard. I'm not going to go do that. I'm a chip company. That doesn't look like a chip. And so there's a natural, and you have to, in order for you to even prove that something works or not, you're $2 billion into it.
Yeah.
And you turn it on to realize it's not very effective, you're $2 billion and 2 years into it. The risk of exploring something new is too high for the customers, and so a lot of competitors tend to say, you know, we're not into training, we're into inference. Inference is incredibly hard. Let's think about it for a second. The response time of inference has to be really high, but this is the easy part. That's the computer science part. The hard part of inference is the goal of somebody who's doing inference is to engage a lot more users, to apply that software to a large installed base. Inference is an installed base problem. This is no different than somebody who's writing an application on an iPhone. The reason why they do so is because iPhone has such a large installed base. Almost everyone has one. And so if you wrote an application for that phone, it's going to have the benefit of, it's going to be able to benefit everybody. Well, in the case of NVIDIA, our accelerated computing platform is the only accelerated computing platform that's literally everywhere. And because we've been working on it for so long, if you wrote an application for inference, and you take that model and you deploy it on NVIDIA's architecture, it literally runs everywhere. And so you can touch everybody, you can enable, have greater impact. And so the problem with inference is actually installed base. And that takes enormous patience and years of success and dedication to architecture compatibility, you know, so on and so forth.
You make completely state-of-the-art chips. Is it possible, though, that you'll face competition that claims to be good enough? Not as good as NVIDIA, but good enough, and much cheaper. Is that a threat?
Well, first of all, competition, we have more competition than anyone on the planet has competition. Not only do we have competition from competitors, we have competition from our customers.
Yeah, that's true.
And I'm the only competitor to a customer, fully knowing they're about to design a chip to replace ours. And I show them not only what my current chip is, I show them what my next chip is, and I'll show them what my chip after that is. And the reason for that is because look, if you don't make an attempt at explaining why you're good at something, they'll never get a chance to buy your products. And so we're completely open book in working with just about everybody in the industry. And the reason for that, our advantage is several. Our advantage, what we're about, is several things. Whereas you could build a chip to be good at one particular algorithm, remember, computing is more than even transformers. There's this idea called transformers. There's a whole bunch of species of transformers, and there are new transformers being invented as we speak. And the number of different types of software is really quite rich. And the reason for that is because software engineers love to create new things, innovation. And we want that. What NVIDIA is good at is that our architecture, not only does it accelerate algorithms, it's programmable, meaning that you can use it for we're the only accelerator for SQL. SQL came about in the 1960s, IBM, 1970s, in storage computing. I mean, SQL is structured data is as important as it gets. 300 zettabytes of data being created, every couple of years. Most of it is in SQL, structured databases. And so we can accelerate that. We can accelerate quantum physics. We can accelerate Schrödinger's equations. We can accelerate just about fluids, particles, lots and lots of code. And so what NVIDIA is good at is the general field of accelerated computing. One of them is generative AI. And so for a data center that wants to have a lot of customers, some of it in financial services, some of it in manufacturing, so on and so forth, in the world of computing, we're a great standard. We're in every single cloud, we're in every single computer company, and so our company's architecture has become a standard, if you will, after some 30 some odd years. And so that's really our advantage. If a customer can do something specifically that's more cost effective, quite frankly, I'm even surprised by that. And the reason for that is this. Remember, our chip is only part. Think of when you see computers these days, it's not a computer like a laptop, it's a computer, it's a data center. And you have to operate it. And so people who buy and sell chips think about the price of chips. People who operate data centers think about the cost of operations. Our time to deployment, our performance, our utilization, our flexibility across all these different applications, in total, allows our operations cost, they call it total cost of operations, TCO. Our TCO is so good that even when the competitors' chips are free, it's not cheap enough. And that is our goal, to add so much value that the alternative is not about cost. And so we, of course that takes a lot of hard work, and we have to keep innovating and things like that, and we don't take anything for granted. But we have a lot of competitors. Yeah.
As you know, but maybe not everybody in the audience knows, there's this term artificial general intelligence, which basically...
I was hoping not to sound competitive, but John asked a question that kind of triggered a competitive gene. And I came across, I want to apologize, I came across, if you will, a little competitive. I apologize for that. I could have probably done that more artfully. I will next time. But he surprised me with a competitor. I thought I was at an economic forum.
Just walking in here, I asked him, I'd sent some questions to his team. And I said, did you look at the questions? He says, no, I didn't look at the questions because I want it to be spontaneous. Besides, I might start thinking about it, and then that would be bad. So we're just kind of winging it here, both of us. So I was asking, when do you think, and of course, when do you think we will achieve artificial general intelligence, the sort of human level intelligence? Is that 50 years away? Is it 5 years away? What's your opinion?
I'll give you a very specific answer. But first, let me just tell you a couple of things about what's happening that's super exciting. First, of course, we're training these models to be multimodality, meaning that we will learn from sounds, we'll learn from words, we'll learn from vision, and we'll just watch TV and learn, so on and so forth. Okay, just like all of us. And the reason why that's so important is because we want AI to be grounded. Grounded not just by human values, which is what ChatGPT really innovated. Remember, we had large language models before, but it wasn't until reinforcement learning human feedback that grounds the AI to something that we feel good about, human values, okay? And now, could you imagine, now you have to generate images and videos and things like that. How does the AI know that hands don't penetrate through podiums, that feet stand above the ground, that when you step on water, you all fall into it? So you have to ground it on physics. And so now the AI has to learn by watching a lot of different examples, and ideally, mostly video, that certain properties are obeyed in the world. Okay, it has to create what is called a world model. And so one, we have to understand multimodality. There's a whole bunch of other modalities, like, as I mentioned before, genes and amino acids and proteins and cells, which leads to organs and so on and so forth. And so we would like to multimodality. Second is greater and greater reasoning capabilities. A lot of the things that we already do, reasoning skills are encoded in common sense. Common sense is reasoning that we all kind of take for granted. And so there are a lot of things in our knowledge in the internet that already encodes reasoning, and models can learn that. But there's higher level reasoning capabilities. For example, there's some questions that you ask me right now when we're talking. I'm mostly doing generative AI. I'm not spending a whole lot of time reasoning about the question. However, there are certain problems, like, for example, planning problems, where that's interesting. Let me think about that. And I'm cycling it in the back, and I'm coming up with multiple plans. I'm traversing a tree. Maybe I'm going through my graph, and I'm pruning my tree and saying, this doesn't make sense. But this I'm going to play, and I simulate it in my head, and maybe I do some calculations, and so on and so forth. That long thinking, AI is not good at today. Everything that you prompt into ChatGPT, it responds instantaneously. We would like to prompt something into ChatGPT, give it a mission statement, give it a problem, and for it to think a while. Isn't that right? And so that kind of system, what computer science calls system 2 thinking, or long thinking, or planning, those kind of things, reasoning and planning, those kind of problems, I think we're working on those things. And I think that you're going to see some breakthroughs. And so in the future, the way you interact with AI will be very different. Some of it will be just give me a question and answer. Some of it say, here's a problem, go work on it for a while. Okay? Tell me tomorrow. And it does the largest amount of computation it can do by tomorrow. You could also say, I'm going to give you this problem. Spend $1,000 on it, but don't spend more than that. And it comes back with the best answer within the 1,000. Or you could, so on and so forth. Okay, so that's now AGI. The question on AGI is, what's the definition? Yeah. In fact, that's kind of the supreme question. Now, if you ask me, if you say, Jensen, AGI is a list of tests, and remember, an engineer knows that anybody in that prestigious organization that I'm now part of, it knows for sure about engineers, is that you need to have a specification and you need to know what the definition of success is. You need to have a test. Now, if I gave an AI a lot of math tests and reasoning tests and history tests and biology tests and medical exams and bar exams and you name it, SATs and MCATs and every single test that you can possibly imagine, you make that list of tests and you put it in front of the computer science industry, I'm guessing in 5 years' time, we'll do well on every single one of them. And so if your definition of AGI is that it passes human tests,
yep,
then I will tell you 5 years. If you tell me, if you asked it to me a little bit differently the way you asked it, that AGI is going to have human intelligence, well, I'm not exactly sure how to specify all of your intelligence yet. And nobody does, really, and therefore it's hard to achieve as an engineer. Does that make sense? Okay, and so the answer is we're not sure, but we're all endeavoring to make it, better and better.
So I'm going to ask 2 more questions, and I'm going to turn it over because I think there's lots of good questions out there. The first one I was going to ask about is, could you just dive a little deeper into what you see as AI's role in drug discovery?
The first role is to understand the meaning of the digital information that we have. Right now we have all, as you know, we have a whole lot of amino acids. We can now, because of AlphaFold, understand the protein structure of many of them. But the question is now, what is the meaning of that protein? What is the meaning of this protein? What is its function? It would be great, just as you can chat with GPT. As you guys know, you can chat with a PDF. You take a PDF file, doesn't matter what it is. My favorites are you take a PDF file of a research paper and you load it into ChatGPT and you start just talking to it. It's like talking to the researchers. You just ask what inspired this research? What problem does it solve? What was the breakthrough? What was the state of art before then? What were the novel ideas? Just talk to it like a human. Okay. In the future, we're going to take a protein, put it into ChatGPT just like PDF. What are you for? What enzymes activate you? What makes you happy? For example, There'll be a whole sequence of genes, and you're going to take and it represents a cell. You're going to put that cell in. What are you for? What do you do? What are you good for? You know? What are your hopes and dreams? And so that's one of the most profound things we can do, is to understand the meaning of biology. Does that make sense? If we can understand the meaning of biology, as you guys know, once we understand the meaning of almost any information that it's in the world of computer science, in the world of computing, amazing engineers and amazing scientists know exactly what to do with it. But that's the breakthrough. The multi-omic understanding of biology. And so that's, if I could, deep and shallow answer to your, I think that's probably the single most profound thing that we can do.
Boy, Oregon State and Stanford are really proud of you. So if I could switch gears just a little bit and just say, Stanford has a lot of aspiring entrepreneurs, students that are entrepreneurs, and maybe they're computer science majors or engineering majors of some sort.
Please don't build GPUs.
What advice would you give them to improve their chances of success?
One of my great advantages is that I have very low expectations. And I mean that. Most of the Stanford graduates have very high expectations. And you deserve to have high expectations because you came from a great school. You were very successful. You're at top of your class. Obviously, you were able to pay for tuition, and then you're graduating from one of the finest institutions on the planet. You're surrounded by other kids that are just incredible. You should have you naturally have very high expectations. People with very high expectations have very low resilience. And unfortunately, resilience matters in success. I don't know how to teach it to you except for I hope suffering happens to you. And I was fortunate that I grew up with my parents providing a condition for us to be successful on the one hand, but there were plenty of opportunities for setbacks and suffering, and and to this day I use the phrase pain and suffering inside our company with great glee, and the reason, and I mean that, boy, this is going to cause a lot of pain and suffering, and I mean that in a happy way. Because you want to train, you want to refine the character of your company. You want greatness out of them. And greatness is not intelligence, as you know. Greatness comes from character, and character isn't formed out of smart people. It's formed out of people who suffered. And so that's kind of the, and so if I could wish upon you, I don't know how to do it, but for all of you Stanford students, I wish upon you, ample doses of pain and suffering.
I'm going to back out of my promise and ask you one more question. How do you seem incredibly motivated and energetic, but how do you keep your employees motivated and energetic when they probably become richer than they ever expected to be?
Yeah, I'm surrounded by 55 people. My management team, so you know, my management team, my direct reports is 55 people. I write no reviews for any of them. I give them constant reviews, and they provide the same to me. My compensation for them is the bottom right corner of Excel. I just drag it down. Literally, many of our executives are paid the same, exactly to the dollar. I know it's weird.
It works.
And I don't do one-on-ones with any of them unless they need me. Then I'll drop everything for them. I never have meetings with them just alone. And they never hear me say something to them that is only for them to know. There's not one piece of information that I somehow secretly tell e-staff that I don't tell the rest of the company. And so in that way, our company was designed for agility, for information to flow as quickly as possible, for people to be empowered by what they are able to do, not what they know. And so that's the architecture of our company. I don't remember your question, but I got it. John, no, I got it. And the answer for that is my behavior.
Yeah.
It's how do I celebrate success? How do I celebrate failure? How do I talk about success? How do I talk about setbacks? Every single thing that I'm looking for opportunities to instill every single day. I'm looking for opportunities to keep on instilling the culture of the company and what is important, what's not important, what's the definition of good? How do you compare yourself to good? How do you think about good? How do you think about a journey? How do you think about results? All of that, all day long.
Mark, Duggan, can you help us? Okay, yeah. Good.
So let's open it up for some questions. Let me start with Winston, and I'll come to you. Oh, we need a microphone. Can you just, Ben, you got this? Yep. Board member Winston Chen.
I have a couple questions. What's the story about your leather jacket? And the second is, according to your projection and calculation, in 5 to 10 years, how much more semiconductor manufacturing capacity is needed to support the growth of AI?
Okay, I appreciate 2 questions. The first question is, this is what my wife bought for me, and this is what I'm wearing. and because I do 0% of my own shopping, as soon as she finds something that doesn't make me itch, because she's known me since I was 17 years old, and she thinks that everything makes me itch. And the way I say I don't like something is it makes me itch. And so as soon as she finds me something that doesn't make me itch, if you look at my closet, the whole closet is a shirt. Because she doesn't want to shop for me again. And so that's why this is all she bought me, and this is all I'm wearing. And if I don't like the answer, I can go shopping. Otherwise, I can wear it. And it's good enough for me.
Okay, we've got
second question on this, the forecast is actually I'm horrible at forecasting, but I'm very good at first principled reasoning of the size of the opportunity. And so let me first reason for you. I have no idea how many fabs, but here's the thing that I do know. The way that we do computing today, the information was written by someone, created by someone. It's basically pre-recorded. All the words, all the videos, all the sound, everything that we do is retrieval-based. It was pre-recorded. Does that make sense? As I say that, every time you touch on a phone, remember, somebody wrote that and stored it somewhere. It was pre-recorded. Okay? Every modality that you know. In the future, because we're going to have AIs, it understands the current circumstance, and because it's tapped into all of the world's latest news and things like it's called retrieval-based. Okay? And it understands your context, meaning it understood why you asked what you're asking about. When you and I ask about the economy, we probably are meaning very different things and for very different context. And based on that, it can generate exactly the right information for you. So in the future, it already understands context, and most of computing will be generative. Today, 100% of content is pre-recorded. If in the future 100% of content will be generative, the question is how does that change the shape of computing? And so, without torturing you anymore, that's how I reason through things. How much more networking do we need? More or less of that? Do we need memory of this? And the answer is we're going to need more fabs. However, remember that we're also improving the algorithms and the processing of it tremendously over time. It's not as if the efficiency of computing is what it is today, and therefore the demand is this much. In the meantime, I'm improving computing by 1 million times every 10 years, while demand is going up by 1 trillion times. And that has to offset each other. Does that make sense? And then there's technology diffusion and so on and so forth. That's just a matter of time. But it doesn't change the fact that one day, all of the computers in the world will be changed, 100%. Every single data center will be, all of those general purpose computing data centers, 100% of the $1 trillion worth of infrastructure will be completely changed. And then there'll be new infrastructure built on, even on top of that.
Okay, next question right here, Ben. And then over here to Randy. So, yeah.
Thanks for coming today. So recently you said that you encourage students not to learn how to code.
Yeah.
And if that's the case, it means one of maybe a few things, but do you think the world starts to look like, from a company formation and entrepreneurship perspective, that it goes towards many, many more companies that are created? Or do you think it's consolidation to just a number of the big players?
So first of all, I said it so poorly that you repeated back poorly. I didn't, if you would like to code, for God's sakes, code, okay? If you want to make omelets, make omelets. I'm not you know, coding is a reasoning process, it's good. Is it going to guarantee you a job? No, not even a little bit. The number of coders in the world surely will continue to be important, and NVIDIA needs coders. However, in the future, the way you interact with the computer is not going to be C++ mostly. For some of us, that's true. For some of us, but for you, you know, why program in Python? So weird. In the future, you'll tell the computer what you want, and the computer will you say, hi, I would like you to come up with a build plan with all of the suppliers and bill of material for a forecast that we have for you. And based on all the necessary components necessary, come up with a build plan. Okay? And then if you don't like that, you just write me a Python program that I can modify of that build plan. And so remember, the first time I talk to the computer, I'm just speaking in plain English. The second time, so English, by the way, human, it's the best programming language of the future. How you talk to a computer, how do you prompt it? It's called prompt engineering. How you interact with people, how do you interact with computers? How do you make a computer do what you want it to do? How do you fine-tune the instructions with that computer? That's called prompt engineering. There's an artistry to that. Okay, so for example, most people are surprised by this, but it's not surprising to me, but it's surprising. For example, you ask Midjourney to generate an image of a puppy on a surfboard in Hawaii at sunset. Okay, and then it generates one. And you say, oh, more cute. Make it more cute. And it comes back, it's more cute. And you go, no, cuter than that. And it comes back. Why is it that software would do that? There's a structural reason why it does that. But for example, you need to know that capability exists in a computer in the future. Isn't that right? That if you don't like the answer first time, you could fine tune it and get it to within the context that you can make it give you better and better results. And once you can even ask it to write the program altogether to generate that result in the future. And so my point is that programming has changed in a way that is probably less valuable. On the other hand, I will tell you this, that because of artificial intelligence, we have closed the technology divide of humanity. Today, about 10 million people are gainfully employed because we know how to program computers, which leaves the other 8 billion behind. That's not true in the future. We all can program computers. Does that make sense? You all know how to prompt a computer to make it do things. And all you have to do is look at YouTube and look at all the people who are using prompt engineering, all the kids and who are making it do amazing things. They don't know how to program. They're just talking to ChatGPT. They just know that if I tell it to do this, it'll do that, And so it's no different than interacting with people in the future. That's the great contribution the computer science industry has made to the world. We've closed the technology divide.
That's inspiring. Okay, over here, we've got that. Sounds very good. We've got Randy with a question right over here.
Thank you very much. I'm just wondering do you think very much about geopolitical risk, and how do you see it impacting your industry, if you do?
Geopolitical risk, we are almost the poster child of geopolitical risk. And the reason for that is because we make a very important instrument for artificial intelligence, and artificial intelligence, as John and I were talking about earlier, is the defining technology of this time. And so the United States has every right to determine that this instrument should be limited to countries that it determines that it should be limited with. And so the United States has that right, and they exercise that right. And your question has to do with what is the implication to us. First of all, we just have to understand these policies, and we have to stay agile so that we can comply with the policies, number one. On the one hand, it limits our opportunity in some places, and it opens up opportunities in others. One of the things that has happened in the last, I would say, maybe even 6 to 9 months, is the awakening of every single country, every single society, the awakening that they have to control their own digital intelligence. That India can't outsource its data so that some country transforms that digital data into India's intelligence and imports that intelligence back to India. That awakening, that sovereign AI, that you have to dedicate yourself to control your sovereign AI, your sovereign intelligence, protect your language, protect your culture for your own industries. That awakening, I think, happened in the last 6-9 months. The first part was we have to be mindful about safety. Then the second part was, hold on a second, we all have to do this. And so every single country from India, Canada's doing this, the UK, France, Japan, Singapore, Malaysia, the list goes on. Just about every single country now realize that they have to invest in their own sovereign AI. So geopolitics, in the one hand, limited opportunities, but it created just enormous opportunities elsewhere. And so, hard to say.
Okay, so I think I have multiple hands, but I have time for one more question. I am going to go right here. You were further in the queue.
Now remember, the last question has big pressure. Do you guys agree with that? Can we all agree?
Right here.
The person who asked the last question, don't leave us all depressed. Don't trigger me, please. That's all I'm saying. I'm just kidding.
I'm going to invoke your commandment to have low expectations at this juncture. You mentioned you're competing with your customers, and I'm wondering, given the advantages that you have, why they're doing that. And I'm wondering if in the future you see yourself building more customized solutions for customers of a certain scale, as opposed to the solutions that you have now, which are more horizontal.
So are we willing to customize? The answer is yes. Now, why is it that the bar is relatively high? The reason why the bar is high is because each generation of our platform, first of all, there's a GPU, there's a CPU, there's a networking processor, there are 2 types of switches. I just built 5 chips for one generation. People think this is one chip, but it's 5 different chips. Each one of those chips are hundreds and hundreds of millions of dollars to do. Just hitting launch, which is tape out for us, launching a rocket is several $100 million each time, okay? And I got 5 of them per generation. Then you've got to put them into a system. And then you got to put, you've got networking stuff, you got transceiver stuff, you got optics stuff, you got a mountain of software to do. It takes a lot of software to run a computer as big as this room. And so all of that is complicated. If the customization is so different, then you have to repeat the entire R&D. However, if the customization leverages everything and adds something to it, then it makes a great deal of sense. Maybe it's a proprietary security system. Maybe it's a confidential computing system. Maybe it's a new way of doing numerical processing that could be extended. We're very open-minded to that. And our customers know that I'm willing to do all that and recognizes if you change it too far, you've basically reset. And you've squandered, the nearly $100 billion that's taken us to get here to redo it from scratch. And so they want to leverage our ecosystem to the extent that will be done. I'm very open to it. Yeah, and they know that. Yeah.
Okay, so with that, I think we need to wrap up. Thank you so much to John and Jensen.